Hello to you from Chem Help ASAP. Let's talk about the SN2 reaction. So on the screen in the upper left we have just a kind of a model reaction in which we have a secondary halide interacting with a nucleophile, and we're getting replacement of that halide by the nucleophile. So it's a replacement, it's a substitution. It involves a nucleophile reacting with our substrate, our halide, so it's a nucleophilic substitution. And it may not be apparent from what I've drawn, but it's bimolecular in the rate determining step. That's the 2, the bimolecular 2 in the SN2. On the right we have our reaction coordinate. Note that the reaction, we begin with our starting material, we finished with our products, and this is a one-step process. It just goes through a transition state. So it's one step. There are no intermediates. So if you're looking at a reaction and it shows intermediates like a carbocation or a carbanion on the pathway, it is not an SN2 reaction because everything happens in one step at the same time we go over this energy barrier and come back down. So let's look at a sample reaction. Here we have an alkyl halide. In this case, it's a primary halide instead of a secondary halide. And we react this with sodium cyanide. Sodium cyanide is a salt. Sodium is the cation, and cyanide is an anion, and that carbon has a lone pair. That is our nucleophile. Nucleophiles tend to be electron-rich. It's not multiple nucleophiles, it's just a nucleophile. It has a lone pair. Most nucleophiles are anions, good nucleophiles anyway. And this is a very strong nucleophile, which is characteristic of an SN2 reaction. Now, what does that nucleophile want to do? It wants to attack something that's electron poor. As it turns out, because of polarization of this carbon-bromine bond, that carbon has a partial positive charge. The bromine is partially negative. Polarization of that bond allows our strong nucleophile to be attracted and to attack that carbon. So what we're drawing with that mechanism arrow is the formation of a carbon, a new carbon-carbon bond between this carbon of cyanide and the carbon of our halide. Now that carbon already has 4 bonds. We haven't drawn 2 hydrogens, but there are 2 hydrogens. It has 4 bonds. So in order to keep from expanding our octet, we have to break an old bond, and this bromine then accepts the electron density in this carbon-bromine bond, and it leaves. So the halide has served as our leaving group. We now have the cyano group attached to this key carbon of our halide, and we get sodium bromide as our product, and that is also a salt. You can draw it as a neutral complex or put charges on it, whatever you want, but that will be waste. So here's what we get. So what are the key points about this reaction? Well, we need a good nucleophile. To do an SN2 reaction, you must have a good nucleophile. And we'll have to talk later about how do you identify a good nucleophile. But you need that nucleophile to be strong so that it will attack this partially positive carbon. So this is a strong nucleophile. That makes this species, our halide, an electrophile. And it's kind of a weak electrophile. It only has a partial positive charge. So we need a strong nucleophile partnered with a weak electrophile. Our second main point, the SN2 reaction is sterically sensitive. The more substitution you have around the halide, the slower this reaction gets. In fact, if you try to do this on a tertiary halide, it will not work. So we can't put too much stuff around this reactive carbon or else our nucleophile can't get in there. So that's the SN2 reaction. If there's one thing I want you to take away from this video, to do an SN2, you must have a good nucleophile.